Hello and welcome back. In this video, we are going to review the five-step process of hypothesis testing, but in a case where uh, the population standard deviation is known and we are looking at a two-tailed test. In our previous discussion, we looked at a similar incident, but we were looking at only a one-tailed test, which was an upper-tailed test. Here, we're going to look at a two-tailed test where it's not just limited to one side of the curve, but two sides. Let's do that with a motivating example here. So the production line of Glow toothpaste is designed to fail with a mean weight of 6 ounce. Okay, so right off the bat, we've been given the average weight of the population, and the average weight of the population, according to our question here, is 6 ounce, right? So as you read the question, you can start writing the parameters and their associated values. Periodically, a sample of tubes will be selected in order to check the filling process. Assume that a sample of 30 toothpaste tubes, right? So we have our sample size given to us, and our sample size we represent as n, and that has been given to us to be 30 toothpaste tubes. So our 32 toothpaste tube provides a sample mean of 6.1. We represent sample mean as x bar, and according to the scenario, the sample average is 6.1. No, I'm sorry. Okay, so our sample average is 6.1. The population standard deviation is believed to be 0.2. So we also have our population standard deviation. Like I said earlier, we're still dealing with cases where the population standard deviation is known and that population standard deviation is given to us to be 0.2. Now, take a look at something here. Perform a hypothesis test at a 0.03 level of significance. And so our level of significance is not always going to be 0.05. In this case, we're looking at a zero point zero 0.03 level of significance to determine whether the filling process should continue operating or be stopped. Now, the first thing we do is to state the null and alternative hypothesis. The production line is claiming that a toothpaste tube should have an average weight of 6 ounces. And so our null hypothesis will be that the average weight of a toothpaste tube is 6 ounces. The alternative hypothesis, like we said, is always going to be a statement opposite to the null hypothesis. And so if the null hypothesis is claiming that the weight is 6 ounces, the alternative will be the opposite of that, and that's going to be not equal to. This here presents a two-tailed test because when we say not equal to, what we are actually saying is we don't believe it to be equal to 6. We actually believe that it could be less than 6 or greater than 6. So we specify our null and alternative hypothesis. The next thing we're going to do is to state the significance level. This time we are not dealing with a zero point zero 0.05, but we are dealing with a zero point zero 0.03. So our benchmark at which we would decide to reject the null hypothesis is 0.03. Using our central limit theorem formula that we already know and the values of the statistic and the parameters that we already know, we will find our test statistic value Z, which will be 2.47. Next thing we're going to do is we're going to go to our standard normal distribution table. 2.47 is 0.99324. Sorry, this time we're looking at 2.74, my bad. Okay, so we come over here and our goal is to look for 2.74 on the standard normal curve. All right, so we locate 2.7 on this side, right there, and then 0.04 on this side here, and that gives us a 2.74, and where these two intersect, 0.99693, that is the area to the lower tail given to us on a curve. And so 0.9969 is the area to the lower tail. Now, because it's a two-sided alternative test, whatever the probability given to us by the table is, we need to multiply this by 2. But let's be a little careful here. 0.99693 is the probability given to us by the table. If we multiply this value by 2, it's going to give us a value that is way greater than 1. Actually, when we multiply the 0.99693 by 2, what we are actually looking at is a value of 1.99386. The p-value is a probability, and probability can never be greater than 1. And so if we decide to multiply this value by 2, it's going to give us a value way greater than 1, and that is not acceptable. And so what we do is we take the probability that the table gave us, we first subtract it from 1 so that it gives us a smaller probability, and then we multiply that by 2. And so technically, we don't just go with whatever the table gives us. We first subtract it from 1 if it is greater, to the point where when we multiply by 2, it's going to give us a probability greater than 1. So we subtract it from 1 and then we multiply by 2. When we multiply 2 by 0.9969, it's going to give us 0.0062. This value here therefore becomes our p-value, and we make our decision based on this p-value here. So we'll multiply the 0.9969, we subtract it from 1, it gives us a lower probability of 0.0031, and then we'll multiply by 2 to arrive at the p-value of 0.0062, as you see here. Now, the last step is to conclude whether we have enough evidence to reject the null hypothesis. When we compare our 0.0062 with a significance level of 0.03, our p-value is less than the significance level. Why? Because 0.3 will be at the top here. The p-value is going to be here. Because it's less than 0.03, we will reject the null hypothesis. Very important. You need to understand when we reject the null hypothesis. We reject the null hypothesis when the p-value is less than the significance level. In our example, the p-value is 0.0062, way less than the significance level of 0.03. Therefore, we reject the null hypothesis. Let's illustrate that on the curve here. Because it's a two-sided alternative test, when we got 2.17, we are looking at this side of it, and we are also looking at this side of the negative 2.17. Our probability where we will reject is half here and then half here. Our significance level was 0.03, so we split the 0.03 into 2. On one side, we get 0.015. On the other side, we get 0.015. The p-value, again, when we split into 2, is 0.0031 on here, 0.0031 on here. But together, the p-value is 0.0062. And because 0.0062 is less than 0.03, we reject the null hypothesis. Whenever you get time, practice this. But if you are not able to practice, meet us in class and we will discuss this. Again, like I said, it's always good to practice, and then when you come to class, you compare your answer with the class. Okay. No, we don't usually encourage this, and I don't want to see you do this on the finals, because it's not usually a right approach, but it's also another possible way to conclude for a two-sided test of hypothesis. The approach says that if I have to perform a two-sided test, just like we did over here, all you can also do is you can just find a confidence interval as was discussed in chapter 8. So if you don't remember confidence interval, just review the lecture video on chapter 8. And the lecture video on chapter 8 will tell you that confidence interval estimation basically gives us two values within which we hope to see the population average. The cool thing is, remember in this example, we said the population average is equal to 6. So we know from our null hypothesis that the average of the population is equal to 6, right? Now, to use confidence interval to arrive at the same conclusion, what we do is we calculate the two values within which we hope to see the population average. And these are the two values, 6.02076 and 6.17924. If the population average is a number we see between these two numbers, then it means we can accept the null hypothesis, right? And so the two numbers are what we see here. Let's call this A and let's call this B. And so these are the two boundaries we have, A on the lower tail and then B on the upper tail, right? If this value here can be located between these two numbers, we accept the null hypothesis. But remember, A is 6.02, and so that means the average value of 6 will be less than the boundary A. And because it doesn't fall within these two numbers, we reject the null hypothesis. So it's not something I encourage you to do, but it's another way we can decide whether to reject or not reject the null hypothesis for a two-sided test. This approach only works for two-sided tests and not for one-sided test. Okay, so far we've looked at how to perform a hypothesis test for Z distributions. I want us to look at another scenario where the population standard deviation is unknown. Like we did discuss in chapter 8, considering confidence interval estimate for a normal Z distribution and normal T distribution. The same applies here. In the case where the population standard deviation is unknown, what we do basically is to assume the sample standard deviation. And that presents what we call a T distribution with a degree of freedom equal to n minus 1. Let's look at, again, another 5-step process on how to perform hypothesis test for T distributions. An example to help us do this is what we see below. A state highway patrol periodically samples vehicle speed at a various location on a particular highway. The sample of vehicle speed is used to test the null hypothesis. So the good news is we've been given our null hypothesis. And our null hypothesis is that the average speed is less or equal to 65. What do you think, in your opinion, will be the alternative hypothesis to this null hypothesis? Remember, the null hypothesis is that the average speed is less than or equal to 65. What do you think will be the alternative hypothesis? Good. The alternative hypothesis is greater than 65 because the alternative hypothesis is always a statement against the null hypothesis. So if the null is saying it's less than 65, the alternative will be greater than 65. Now let's get our sample data. So the locations where HO is rejected are deemed to be the best location for radar trap because that's where the speed is greater than 65. At location F, a sample of 64 vehicles. So we know our sample size, and 64 vehicles shows a mean speed of 66.2 miles per hour. Our mean speed of the sample is the sample average, and that is 66.2 miles per hour with a standard deviation of 4.2 miles per hour. So our standard deviation of the sample and not the population, right? Because if we're talking about a sample, it says a sample of 64 vehicles shows an average speed of 66.2 with a sample standard deviation of 4.2 miles per hour. Let's use a significance level this time. We are back to significance level of 0.05 to test the hypothesis. So we're going to go over the 5-step process. Step 1, we state the null and alternative hypothesis. Step 2, we specify our significance level. Now, step 3 is going to be a little different because this time we don't know the population standard deviation. And so what we do, we use the sample standard deviation. The values are already submitted here. The sample size n is 64. The sample average is 66.2. Our standard deviation of the sample is 4.2. And we are using a significance level of 0.05 and a population average of 65. So we slot in these values and it gives us a test statistic T to be 2.29. Look at the difference. In previous example, we were looking at a test statistic Z, but because here we don't know the population standard deviation, we are assuming the sample standard deviation as an unbiased estimator, and therefore we are looking at a T distribution. We take our T value of 2.29. The degree of freedom will be 64.1, and this time we are not using the Z table, we are using the T table. So let's look at a T table here, and our T table, according to the one I have here for a one-tail test, because the T value is 2.29, degree of freedom will be 64 minus 1, which is 63. We will go on to our T table, look up 63. Because we don't have 63, we will look at a number closer to 63, and that is 60. Match that up with our T value, and the T value again was 2.29, and so we will locate 2.29 here, and 2.29 will be between 2.0 and 2.390. For a one-sided test, which is a one-tail test, we are looking at a p-value between 0.025 and 0.01. And so our p-value will be a value between 0.025 and 0.01. Whichever one you decide on, the p-value is less than the significance level of 0.05. And so what will be our conclusion? Because it's less than the benchmark, we reject the null hypothesis. A lot of times students come to me and say, hey, Jonathan, I'm confused. How do we conclude? Think of the significance level alpha as the benchmark, okay? This is where we must meet. If our level doesn't get to this level of 0.05 and we only get to 0.01, we reject the null hypothesis. It's very simple, and a lot of you actually use it. You see, some ladies or some guys have a benchmark they want their partners to reach. If the partner doesn't reach that benchmark, most cases they will reject the partner. I was watching a video on the Indian Army, and if a person wants to get into the Indian Army, you have to go under a horizontal bar. So something like this, right? And the horizontal bar could be set up at a height of 0.05. This is our benchmark. And so in the documentary, if a person comes in and the person is shorter than the Indian Army requirement on height, what they do is they will reject the person's application. But if the person comes in and they are taller than the height, they get accepted into the Indian Army. And so it's very simple, right? Take a look at the p-value as the height of the person, and the significance level is the benchmark. If the person meets that height, they get accepted. If they don't meet it, they get rejected. In our case here, the p-value was 0.01, very lower than the 0.05 significance level. So what would be our conclusion? We reject the p-value. We reject the null hypothesis. And that basically means we don't agree with this statement. We technically agree with the alternative hypothesis. Now, again, it's the same thing. The t-value gives us a significant p-value less than 0.01. Our significance level is 0.05. Therefore, we reject the null hypothesis. I want us to look at a practice question, spend some time on it and work on it. Uh, but when we meet in class, we will discuss the practice question again. So to close off everything, we have a third hypothesis testing scenario, and that's going to be for proportional distributions. Proportional distribution is basically looking at instances where we don't have the average of a sample in the population or the standard deviation of the sample in population. We are dealing with a proportional distribution, a case where we number or we count the number of people that favor a certain ideology versus those who do not favor a certain ideology. And so let's get right into it. The good news though is the steps for proportional distribution is the same as the steps for t distribution and for z distribution. However, here, proportional distribution after stating your null and alternative hypothesis, proportional distribution test statistic is going to be z equal to the sample proportion minus the population proportion divided by the standard deviation of the sample proportion, which is based on this formula here. Let's look at an example and that could help us perform the test. For a Christmas and New Year's week, the National Safety Council estimated that 500 people will be killed and 25,000 injured on the nation's road. Unfortunately, that's a very sad story. But the National Safety Council is claiming that 50% of the accident will be caused by driving. And so already we know what our null hypothesis is. Our null hypothesis is that a proportion of 0.5 or 50% of accident will be caused by drunk driving. We do not believe that. We think maybe it is not, it's less or it could be more, but we don't know. And so we perform a two sample hypothesis test of the proportional distribution. What did we do? After not believing the null hypothesis that is equal to 50%, we take our own sample of 120 accidents, which represent our sample size n, and it showed that out of the 120, an X value of 67 were caused by drunk driving. Let's use this data to test the NSA claim with an alpha value of 0.05. And so we start with the null hypothesis and alternative hypothesis, where we say the null hypothesis is that zero point 0.5, as per the claim of the National Safety Council, right? 0.5 of the accident to be caused by drunk driving against the alternative hypothesis that not 0.5 will be caused by drunk driving. And so we don't know what the actual percentage is, but our alternative hypothesis is saying we do not believe what the null hypothesis is saying. Step 2, we specify our significance level. Step 3, we find our z value. The formula says your sample proportion, and remember our sample proportion p hat. Okay, in some books they can use the bar, some books they use the hat. Our sample proportion p hat will be equal to the count of 67 that was caused by drunk driving divided by the total sample of 120. And so that will give us our sample proportion minus the population proportion, which is claimed from the article to be 0.5, divided by the standard deviation of the sample proportion. Now, for the sake of time, it's already been calculated here. 0.5 into bracket 1 minus 0.5 divided by 120 or square root. And so our standard deviation of the sample proportion is 0.04. See there, look at the z value, 1.29. And so when we go into our z table, the 1.2 now will be equivalent to 0.08997. Now let me ask you a question. Why did we subtract it from 1 first? And then why did we multiply by 2? We subtracted it from 1 because when I multiply 0.8997 by 1, it's going to give me a value greater than 1, and that is not how we do it. And so we first of all subtract the p-value from the table, which is 0.8997, from 1, and then we'll multiply the answer by 2. And so that will give us a p-value of 0.2006. When we compare to our significance level, take a look at that. The p-value is greater than the significance level. And so we accept the null hypothesis. That means we believe what they are quoting to us here. We will not reject the null hypothesis. Okay. Now, I'm going to quickly go over type 1 and type 2 errors, not too important for the test, but when we reject a true null hypothesis, that is a type 1 error. The probability that the null hypothesis is true, but you continue to reject it because you made a mistake and not the null hypothesis, that constitutes a type 1 error. A type 2 error, on the other hand, is when the null hypothesis is false, but you accept it. Right. And so with type 2 errors, what we are basically looking at is the ability to decide whether the null hypothesis is false. Because if the null hypothesis is false and you mistakenly accept it, you've committed a type 2 error. I have a table here to help you understand it. See, when the null hypothesis is true and we accept it, we've made a correct conclusion. If the null hypothesis is false, is true, and we reject the true null hypothesis, we have committed a type 1 error. And the converse is the same. When the when null hypothesis is not true or false, and we accept it, we've committed a type 2 error. But when we reject it, we've made an accurate conclusion. Okay, so this brings us to the end of our lecture video presentation. I'd like you to go over it, try your hands on the practice questions. After you've read or watched the example on how I solve it at the in the presentation, try your hands on the practice question, bring it to class, let's discuss it, and have a rest of a wonderful day. Thank you, and I will see you in the next video.